Hello, back again with another episode in message passing object oriented programming with the R6 package. This time we're just going to show a somewhat more elaborate program in the object oriented style. It's going to be a simulation model for population growth for whales in an ocean. I caution you in advance that this is not the most efficient way to write a simulation model. But it's a bit tempting to write it in the object-oriented style because you can think of the ocean as an object and whales as objects that are part of this ocean object. So let's give it a try. So in our model, the whales are mostly solitary creatures, and they move randomly around the ocean. Feeding on plankton or whatever. And when a male and female whale are close enough together, then they're going to, then the female whale is going to check the male to see if he's mature enough to mate. And if she herself is fertile, then she'll mate with him and a child will be produced. Now that child could be either male or female, with equal likelihood for either sex. But after mating, the female will be infertile for a period of time while she's essentially taking care of her child whale. Whales are also going to have a maximum lifetime. And then in any time period in this model, it's going to be possible for a whale to starve, okay, causing it to die before it reaches its natural lifespan. The probability of starvation is going to be a function of the population at the moment. It's going to be low when the whale population is small, presumably because there's a large amount of food for each whale. But the starvation probability is going to increase directly proportional to the size of the population. So once the population gets high enough, then the starvation rate might be higher than the birth rate. So you can sort of imagine what might happen. That the population, if there's enough whales to actually sort of meet each other and mate before they die, then the population will rise eventually, perhaps to some stable level where the birth rate and the starvation rate are equal. On the other hand, if the population ever dips low enough that the whales have, so much trouble finding each other that the birth rate, is low enough so that it can't replace the whales as they die, then the population would die out. So we're going to implement our simulation with an ocean object and with a whale object, and there being two, an ocean class, I should say, and a whale class. There's going to be two classes that inherit from whale, male whales and a female whale. So we're going to start by defining the class whale. And as I go through this, I'm not going to give a complete detailed description of how the code works, just a brief overview of main points, because the presumption is that you're going to be reading the text again for yourself and making a more detailed study of it all. But anyway, the whale class has a number of public methods and a number of public attributes and methods. And the attributes include the position of the whale at any time, its age, which will change, one more unit of age for every time period in the simulation. It's going to have a natural lifespan. It's going to have a range, and that is a distance such that it can detect whales that are within that distance. It's going to have a certain age at which it becomes mature and able to mate. And it's going to have a certain step size, which is how far it moves during one time period in the simulation. There's an initialize function for the whale as well. Now, just to break up the programming a bit, I'm adding on another attribute of the function, the method move. So it's public. Its name is move, and this is the function where the whale makes its move during that unit time period from one position to another. It's basically the whale chooses a direction randomly determined by this variable theta here, and it moves a step side in that direction provisionally. But there's a check to see if that putative new position is still within the boundaries of the ocean. And so basically a new putative position will be chosen repeatedly until that position does check out as within the ocean, and then we'll break out of that repeat loop. And the self position that is assigned at that point becomes the whale's new position. For the move function, there was a parameter dims up here, and those are the x and y dimensions, the length and width, as it were, of this ocean on the xy axis. So that the dims is going to come from the ocean. Is going to come from the ocean itself. So don't worry about it. We're going to need our male and female whales. Sorry, that's a bit too large. So we're going to need our male and female whales. A male whale is going to inherit from the class whale, and the only thing we really add on is a sex attribute, which is set at male. For female whales, the female is just more complex. They do inherit from whale, but in addition to a sex attribute, which is set at female, they've got a time to fertility attribute and an infertility period. So if it's set at 0, that means as soon as the whale is that means the whale is ready to mate, at the moment, and that value can be changed as the simulation goes on. In addition, we're going to add another method on to the female whale class, and it's going to be a method that allows the female to detect whether a mature enough male is within her range of detection. And so the function here does that checking, and its name is male near. You'll notice in the code for that function, when you study it, that there's an iteration, there's a for loop that iterates through males, and that iterable is actually a list of all of the male whale objects in the ocean. So those are going to be provided by the ocean object when this method is called. And the dist function that you see here is also provided by the ocean, and it's a function for computing the distance between any 2 points in the ocean. Another thing that a female needs, of course, is a function to actually mate should she find a nearby sufficiently mature male. And so here comes the mate method. And what happens is the sex of the baby is randomly sampled from female and male. And when the female mates, her time to fertility is going to be set back to whatever her infertility period is. Like if it's 5 years, then time to fertility will go to 5 years, and that would be the number of that'd be the number of time periods that she's taking care of her baby. Now, what's returned is the baby sex, and that's the information needed to, figure the population over the next time period. It's time to define the ocean class, and it's, quite a large bit of code, especially the initialize function, where you've got to specify how many male whales and how many female whales you want, and you've got to specify the size of the ocean, the x-axis size, the y-axis size. There's also a starvation parameter that you get to set. And the starvation parameter, you'll see how it's used when you study more of the methods of the ocean. Basically, it's a number such that the bigger it is, then the greater is the chance that any individual whale will starve to death in a given time period. So in addition to just setting up the ocean class, we need to endow that class with a method to advance its state 1 unit of time, whether that be a month or a year, however you want to conceive it. And during that unit of time, some things need to happen. Every mature male and female, every mature and fertile female whale has to check for nearby mature males and mate with one if possible and produce a baby. So that's a pretty complex process. Any of the offspring produced have to be added to the ocean's lists of male and female whales. And then the ocean is going to subject every whale to a certain possibility of starvation within that time period. And so some of the whales will be knocked off, the list, the population, but all the whales that survive need to make one of their random moves. And also the age of each whale has to be increased by a time unit. And for females, the time remaining until fertility also has to be decreased by a unit, of course, unless it's 0, in which case it'll stay at 0. So here comes the advance method, yet another public method added on with the set function, the set method to the ocean class that takes care of all of that business. So again, quite a lengthy bit of code to study, but it would certainly reward the process of study. And we want to give the ocean one more method called plot. This is, if called, the plot method is going to produce a little picture of the ocean at a given moment in the simulation, where there are going to be dots in the plot that signify whales at the positions that they have within the ocean. The males are going to be colored red, the females are going to be green. Mature whales that can mate, they're going to appear as larger circles, whereas the little baby whales are going to appear as smaller circles. And rather than use ggplot2, we're going to use R's BasePlot function and its associated helper functions to make our plots so that they can be made quickly, and so a sequence of them can be shown quickly in a kind of animated fashion during a simulation. So again, we'll just let you look at that code for the relatively unfamiliar base plotting capabilities of R. And lastly, we want to put this all together to write a simulation function. And this function is going to allow the user to specify the number of time units that the simulation will cover with a parameter called steps. And the user is also going to have an option to animate the simulation, or to just let the simulation run and then look at a graph of the population over time at the end of the simulation. Notice the user can also set a random seed if they wish, and the user can set how many males and how many female whales are going to be in the ocean at the time 0 of the simulation, and the user gets to set the starvation parameter. And so the OceanSim function is first going to handle what to do about the random seed. And then once it's passed that, it's going to instantiate a member. It's going to instantiate an example of the class Ocean and call it, lowercase Ocean. The dimensions are 100 by 100, and the number of males in the ocean is going to be set to the number of males provided by the user by the parameter up here. The number of females in the ocean is set to the value of the female parameter provided, again, by the user. The starvation parameter for the ocean is also provided up by the value of the starvation parameter for the user in the OceanSim function. We're setting up a little results vector here, population, a numeric vector that's steps long. And then for I and 1, 2 steps, we're just going to conduct the simulation. So inside the for loop is what you need to do to move time along 1 unit. And so the population at any time I is just going to be the male pop in the ocean plus the female population in the ocean. Now, if the animate parameter is true, then you're going to plot the ocean. Now, you want to check if the population at time I is equal to 0. You want to break out of this loop because the simulation is effectively done if the whales have all died off. But if you get past this point, then you'll advance the ocean. And if animate is true, you're going to sleep for half a second. The system is just going to do nothing for half a second, letting the user contemplate that plot. And so that's the for loop, and at the end of it, you're going to have a little vector of the populations at the times 1 through the index I. Remember, the index I might not have reached steps because the population might have died out initially. So this just captures the part of the results vector that's going to have the meaningful population numbers in it. And you make a data frame out of the results and pipe it into ggplot for a nice looking plot. So we're ready for a simulation, and why don't we just try it over in our studio, where I've already got all of the relevant classes and the simulation function in the global environment here. So we'll just run the simulation here. It's going to be 1,000. I'm sorry. Let's try here. It's going to be 200 steps. I'm going to start with 15 male and 15 female whales. Animate's false right now, and I'll just got a random seed of 30, 30. And for some reason, the plot's not showing up. Let me just rerun that thing. It's been a little ticky lately. Do it down the console. Try again. And there we go. And so rather unfortunately, the whales died out after about 140 time units. The population finally dropped down to 0. You can see how we started with a total of 30 whales. They met and mated for a while. The population increased, and then there was a huge dip. And that's because whales have a lifetime of 40 years. That's the way the class sets them up by default. And they start out 10 years old. So around about time 30, there's a big die-off, and basically only the first generation of children is left. And they struggle along for a while, but there just aren't enough of them. So they meet rather infrequently, they mate too infrequently, and their death rate exceeds their birth rate, and the population dies out. At least that's what happened in this simulation. Of course, you can try it again, but if you just take away the seed, then you'll presumably get different results. Again, dying out. Again, dying out. Now, if you want to see things happen in real time, then you can set animate to true. So here I am in my function call starting again with 15 male and female whales in 200 steps, but we're gonna see those steps plotted, and so you can see already a few babies have been produced. They wander around for I think it's 5 time periods, and then they reach their maturity. I believe it's 3 time periods actually. But we've had a die-off of the first generation, and the second generation really just can't keep it going. Looks like they're having trouble finding each other. There's only one female anyway, and she starved or something. Oh, how sad. Lonely whale. Poor lonely whale. And out should come a graph, but I just seem to be having a little trouble with my plotting window lately. It's just not popping up for me. So if you want to try, like initially a larger, maybe a population of males, females, like 75 here, and maybe a lower starvation parameter, lower than the default of 5, how about 2.5, then maybe the population will grow. And if you want, you can try for a lot of steps and just see if the population does grow, does it kind of stabilize at something? So if you want to do that with a lot of steps, you better do animate as false. Let's see what happens here. Waiting patiently. It's a lot of steps. And once the population gets big, it takes a long time to manage each step. So here we go, and it does look like we've essentially stabilized at, well, around 150 whales. See, there's a lot of jiggling back and forth, but it seems like we're at about 150 level, roughly on average. Population did take its initial dip, and it looks like they had a run of bad luck for a while, almost going extinct this time. Wonder what would happen if I ran it again. So if you are interested in exploring this further, the BCSCR package has a more flexible version of the Ocean class where you can set a lot of custom initial populations. Your male and female whales don't all have to be the same type, have the same attributes, and so on. You can have characteristics that vary from whale to whale and make your simulation a little more interesting. So again, I stress the object-oriented approach to the simulation is not necessarily the quickest approach. And also in general, object-oriented programming should be used with some caution. It's very good for large programming projects involving multiple people. For smaller projects like this ocean simulation, it's really not the first thing that you would go to. And there's also a tendency for people when they get into object-oriented programming to sort of make an object out of every sort of concrete thing in their mind, much as I have done here with this whales in the ocean simulation, where it just seems natural to make objects for male whales, objects for female whales, objects for the ocean, objects for everything. But you'll find that in real professional level object-oriented programming, the classes might be quite abstract sorts of things. They might not correspond to sort of natural real-world items. as much as what you see in this example here. So that's it for message passing object-oriented programming in R. The next time that we get together, we'll be examining generic function object-oriented programming, which is really much more natural to R's approach. See you then.